Hey, it's Mr. Shrum. What's up? Are you ready for a biochem? Because that's what's happening right now. Intro to biochemistry, tutorial, objective. You will explain how atoms combine to form larger molecules that have various biological functions. How atoms combine to form larger molecules. Yeah, so easy stuff. Very, very easy. Basic science stuff we're gonna do today. But first, with a warm-up, I'm sure you're used to this setup first. What is your definition of biochemistry? Bio, what does the bio part of biochemistry mean to you? What does chemistry mean to you? What are some of the things that come to your mind? Well, there's a sample answer. Study of the chemical processes that occur in all living organisms. So bio, living, chemistry, chemical processes. How do organic compounds differ from inorganic compounds? So compounds involved with things that are alive versus inorganic compounds, things that are not alive per se. All organic compounds contain carbon. So anytime you've heard in movies or television programs, carbon-based life. Life as we know it is based around carbon. All right. So yes, aliens may exist out in the universe somewhere, and it could be based on another element other than carbon. But here, life as we know it, all organic organisms, compounds, are based on carbon. Here's a little intro video that I'm gonna skip today. You can always go back and watch them. But right now we're on atoms and molecules. This man, I'm sure you recognize him, Albert Einstein, physicist from Germany originally. And of course, the developer of the theory of relativity. And of course, he developed other things too. He was a very prolific scientist. But right now, we're talking about atoms and molecules. So I'm sure you've had a balloon before. You rubbed your hair, and the static electricity built up between them makes your hair look a lot like Albert Einstein. But why does that happen, right? So like, why does rubbing a balloon make hair attracted to the balloon? Well, on the very, very small microscopic atomic level, almost subatomic level, the balloon is stealing electrons from your hair. These electrons, they're super, super tiny, negatively charged particles. And when balloons steal electrons from hair, it makes your hair positively charged. So stealing electrons leaves something positively charged. And what do negative and positive charges do? They are attracted to one another. So the now negatively charged balloon is now attracted to your positively charged hair. And this is all due to the simplest unit of matter, known as atoms. And this is not exactly how they really look, but this is a good visual picture for us to think about atoms and elements and describe neutrons, protons, and electrons, and how protons are positively charged and electrons are negatively charged, and how neutrons are neutral, as you might guess. Anything that occupies space and possesses mass is matter. And the most basic unit of matter, atoms. So take it way back to 5th century BC, before the Common Era. Greek philosophers, I'm going to go with Leucippus and Democritus. They put up a theory that matter is made up of tiny particles that can't be divided further. But we didn't really know until the 1800s that, we didn't have experimental evidence, right? We needed experiments to build our conclusions and to make a stronger argument for the existence of something. And with modern technology, we can prove that atoms exist and are made up of even smaller particles, subatomic particles. Sub because it's beneath the atomic. You get it. You understand how prefixes work. But on the right, we have a chlorine particle, or atom, sorry, a chlorine atom. That's the more technical term for particles. Protons, like we said, positively charged. They're in the nucleus, like the center almost of the atom. Electrons, they're negatively charged. And they're moving around, orbiting all around the nucleus. Neutrons, they do not have a charge, and they're also located in the nucleus. Protons and electrons, they are opposite, and they attract each other. And this attraction gives atoms its structure, all right? And we're given the number of each type of subatomic particle. Protons, 17, 18 neutrons, and 17 electrons. And pay attention to this atomic number, the atomic weight, the number of electrons per shell. And this is how it appears on the atomic, the table of elements. And we'll get into that later. But it's important to note that the number of protons is equal to the number of electrons. And the overall charge is a 0, because positive cancels out negative. Makes sense, yeah? And a substance is made up of only one type of atom, called an element. An element is also called a pure substance. It cannot be broken down further by physical or chemical means. There are about 100 known elements that we know of today. And all types of information such as atomic number, atomic mass, name, and the symbol of the elements is ordered in this table known as the periodic table of elements. It's just a table of elements laid out in periods, and we'll get into why that's the way we refer to them later. But here you see the subcategories: alkaline metals, lanthanides, transition metals, alkaline earth metals, actinide, post-transition metal, metalloid, polyatomic nonmetal, diatomic nonmetal, noble gas. These guys are pretty important. Actually, they all have their perks, right? And here are some of the unknown chemical properties. And how do we name things that we don't know? Well, we'll get into it. Yeah. Next slide. But they are arranged in increasing order of atomic number. So it starts out with 1, 2, 3, 4, and then keeps on going in that order horizontally. The table has 18 vertical columns called groups. Elements of a period have the same number of energy levels for their electrons. For example, all elements in the second row, which is what we call a period, have 2 energy levels. So the second row, they all have 2 energy levels. But on the other hand, the element in the same group, which is the vertical, so we have horizontal periods and horizontal groups. So the ones in the same group have the same number of electrons in the outermost energy level. And these are called valence electrons. And hopefully we see a picture soon so you can remember. Roman numerals above each group represent the number of valence electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8, 8, 8, 8. Actually, this is just hard to see. But we'll get back to it. So remember that valence electrons, they max out. But we'll get into that later. Because of the same number of valence electrons, that makes their chemical properties very similar. So your outermost electron number affects the properties, the chemical properties. And that's why you notice they're grouped together by color, because they have similar properties. And we'll get into much more detail later. Protons, the atomic number tells us the number of protons in the nucleus. Bam. So carbon, 6 protons. Atoms of any element have a fixed number. And that helps us actually identify the atom itself. Carbon has 6 protons, so the atomic number is 6. Neutrons, isotopes are atoms of the same element that have different numbers of neutrons. So you can have an element, you can have carbon with different number of neutrons. So the proton number never changes, but the neutron number does change, or it can. Average atomic mass is the average mass of all naturally occurring isotopes of an element based on their abundance. So the most common isotopes are factored more heavily into the calculation of average atomic mass. So the most common isotope largely determines the mass, okay? So if a isotope has more neutrons, the atomic mass is gonna be larger. But since isotopes of that type are less frequently seen in nature, they're more rare, they only change the mass slightly of the average atomic mass. So here we go. Hydrogen isotopes, they all have one proton. So that means they're all hydrogen. However, you see this one has no neutrons, called protium. Deuterium, that means two, has one, and two as in two particles, one proton and then one neutron. And then tritium, which is like 3 particles, are in the nucleus with 2 neutrons and 1 proton. Mass number does not appear on the periodic table. It's the sum of the number of protons and the number of neutrons. An element's mass number is quite close to the atomic mass, not exactly. From the average atomic mass, we can deduce the most common isotope of an element. So given the average atomic mass, the average is going to be closest to the actual mass of one of these isotopes, the most common one. A proton weighs approximately 1.0073 atomic mass units, or AMU. Neutron, just a little bit heavier, but almost the same. Electron's a lot smaller, less massive. The atomic mass of hydrogen is 1.00794. So what number is closest to that? Hydrogen has 3 stable isotopes: protium, deuterium, tritium. Protium contains only 1 proton. Its mass number is 1. Deuterium contains 1 proton and 1 neutron. Its mass number is 2. Tritium contains 1 proton and 2 neutrons. Its mass number is 3. Okay? So the atomic mass of hydrogen is closest to the mass number of protium. So protium is the most common type. The atomic mass, if that's the average, the closest would be protium, because it's just 1 proton weighing 1.0073. You do have deuterium and tritium, which pulls the average a little higher, but they're not as common. The most abundant type is protium. Protium. Yeah. Try saying that a few times. Oh, yeah. So the first model represents the proton and neutron distribution in the nucleus of 4 helium isotopes. The second image shows the entry for helium in the periodic table. Based on the info in the periodic table, which is the most common isotope of helium? Okay. So here we have 4 helium isotopes. So we see helium, everyone has 2 protons in the nucleus. And then isotopes means they have different numbers of neutrons. All right, so given that helium has an average atomic mass of 4.0026, which isotope is about equal to that? If each proton and neutron weigh about 1, then it would be B. Because this only has a mass number of 3. This one has 4, 5, 6. So this one's the closest one for helium. And it just gives you an explanation. Yeah. Molecules and compounds. So the fun thing, this is where things get interesting, okay? If things are not interesting yet for you, oh boy, then buckle up, right? A molecule is when 2 or more atoms group together by means of a chemical bond. And they consist of atoms of the same element, or well, they can, and that's described as an elemental molecule. But if they're made up of several different elements, they are compounds. Compounds are molecules that form when at least two elements bond together. So consider water, H2O. It's a compound because it is made up of two hydrogen atoms and one oxygen, one big ol' oxygen atom. So all compounds are molecules, but not all molecules are necessarily compounds, right? Because compounds need to be made up of more than one element, remember. And the chemical bond can be several different types, okay? And that is determined by, well, the nature of the bond. And we show that with this visualization tool. There are two types of bonds that are more important to understand at this moment in time. Covalent and ionic. Covalent bonds form when atoms share electrons in the outer energy levels, or shells. That's another word we use. In an atom, the first electron shell can hold up to 2 electrons. So this innermost shell can hold 2. But shell 2 and 3 can each hold 8 electrons. A hydrogen atom has only 1 electron, but its shell can hold 2 electrons. So oxygen has 8 total electrons, 2 in the inner shell, leaving 6 for the outer shell. Because the outer shell can hold 8, it has a strong tendency to fill the places that are empty with 2 hydrogen atoms. So the hydrogen atoms, they don't give up their electron, they just share it, because sharing is caring, right? So usually oxygen, it only has 6, but then it gains this one and this one from 2 other hydrogen atoms. Both oxygen and hydrogen complete their outer shells and become more stable, right? So you see that molecules, they want to become stable, and given the chance, they will bond if that makes them less chaotic and more stable. They want their outermost shell to be filled. And if the bond is shared, it's covalent. However, ionic bonds are a little bit different. Since atoms have an overall neutral charge, the outer energy level has to be completely filled or completely empty. So depending on your outermost layer, it depends, that will determine, sorry, that's a better way to put it. Depending on your outermost layer, however many electrons there are, that determines what kind of bonding will occur. If you're only missing like 1 or 2, you're likely gonna see a covalent bond. But if you have just like a random 1 electron orbiting, that's not a very stable relationship. So that electron will probably be ionically bonded to another molecule. And here you see that sodium chloride. Here's we have this one who has a loose electron that gets ionically bonded to this chlorine. So the gaining and losing of electrons gives charges to these usually normal neutral charged atoms. So you see this sodium is neutral, but this outer electron is not stable, right? And this chlorine, though neutral, it wants to have one more electron to be stable. So sodium chloride, sodium has just one electron in its outermost energy level. It can acquire stability by giving it up. And if you're giving up something that has a negative charge, you will become positively charged. It's like cutting off a toxic negative person will leave you more positive. Think of it like that. And then this molecule, chlorine, is trying to this chlorine atom takes on a toxic friend to fill up its friend group, and that will negatively impact their friend group. That's a metaphor that I think could work here, maybe. But the idea here is that they're both neutral, but then one gives up and one gains an electron, thus giving them a charge that they did not previously have. And since now they have charges, this one has positive and negative, they're attracted to each other. So they stick together now. Though previously they were neutral and they didn't really like hang out, but now they're like, let's hang out. Chemical reactions. So a chemical reaction is a process that involves rearranging atoms or a group of atoms to form new substances. So if we're rearranging, that is going to require bonds that exist already to break up and then form newer bonds. So we are given an example when iron reacts with oxygen in the air, it forms rust. And that is the way we write that out in scientific terms with the elements. At the start of a reaction, substances called reactants undergo a chemical change to form products at the end of the process. So you start out with reactants, bam, and then you have a product. They produce something known as a product. Not all reactions involve chemical change, though. An example of that, boiling only changes water, H2O, from liquid to gas. So boiling does not change the chemical composition of water. Water is still water. It just changes the state of matter. And this change is a physical change. So it is important to recognize the difference between a physical change and a chemical change. Physical change, the appearance may change, but at the small atomic level, chemically nothing's different about the substance. Where in a chemical change, there's deeper change at the atomic level. And for this type of reaction to occur, you're going to need energy. And when you strike a match on the side of a matchbox, it ignites the match, and that's an example of inputting energy. And the minimum amount for this to happen is called activation energy. So to activate a chemical reaction, you need to input enough energy to reach activation energy levels. And the lower the activation energy, the faster the reaction occurs. Chemical bonds can be broken when molecules are in a contorted state called a transition state. Activation energy is required to get the reactant molecules into this transition state. And in the example of striking a match, when you strike a match, this provides the activation energy to the reactants in the match for the reaction to take place. Okay? And now we're going to look at some equations and how balancing equations fit into this picture. So you'll have a simulation to go to. And it will help you balance and understand how the equations, how moving things around will balance the scale of the equation. And it'll ask you a few questions based on your experience in the simulation. What do the numbers 3 and 4 refer to in 3 and H4? So the scales shown in the introduction measure mass, or the amount of matter in a particular object. The scientific law of conservation of mass states that matter cannot be created or destroyed during a chemical reaction, but it can change from one form to another. Did the simulation support the scientific law? Explain why or why not. So in the simulation, did you see that the mass was conserved, right? Did you see anything being created or destroyed? Or did you just see mass being converted into another form? Remember how we talked about precise measurements for accuracy, right? In the game, to explain why precise measurements of reactants is important to form the desired products in a chemical reaction. So why do you need to be precise when when you need to form the desired products in a reaction? Why do we have to be super, super accurate in this case? Based on the simulation, write a definition for the term balanced chemical equation. So why balanced? How do you balance an equation? Like, why do you even want a balanced equation? So this shows the correct molecules form the reaction, but the products are incorrect. How would you correct it? So how do you make these equal these, right? Something is off here. But I'll let you do that. And we will move on to biomolecules. organic typically makes people think of things that are alive, natural, right? Or you see organic products in stores. They want you to think of it as natural, naturally occurring. Inorganic suggests something a little more artificial, human-made, but not necessarily in science. Especially when we're talking about compounds that can be organic or inorganic. Water is incredibly useful and vital for life on Earth, but it itself is not alive. It is inorganic. It was one of the most important inorganic compounds for us. It's inorganic because it does not contain carbon. Organic compounds contain carbon atoms covalently bonded to other atoms, usually in the form of oxygen or hydrogen. Some organic compounds combine to form large macromolecules, macro meaning big, so big molecules that are crucial to life on Earth. Scientists call them biological macromolecules or biomolecules. So life molecules. There are 4 main biomolecules that are essential for life. Nucleic acids are macromolecules that contain genetic information. They transfer this genetic information from one generation to the next. And there are smaller subunits that make up these nucleic acids, and they are called nucleotides, and they link up to each other. And these nucleotides are composed of carbon, hydrogen, oxygen, phosphorus, and nitrogen. Nucleic acid is the hereditary material found in all organisms. In humans, it is present in the nucleus of all the body's cells except for red blood cells. And we'll label those as RBCs, red blood cells. Because they actually lose their nucleus as they mature. Deoxyribonucleic acid, DNA. If you want to sound scientific, just say deoxyribonucleic acid instead of DNA. And it forms a double helix. This is a very common sciencey image. So first we had nucleic acids, nucleotides. Now we have carbs. Everybody loves carbs. I love carbs. Most of the food that we eat contains biomolecules known as carbohydrates. Enzymes within our body break down carbs into smaller sugar molecules that serve as major energy sources for us. So carbs, starches, we have enzymes that bust them down into little sugary molecules, and then our body uses that as energy to stay alive. Carbs contain carbon, of course, right? Hydrogen, because it's in the name, and oxygen. They are generally represented by the empirical formula here. The smallest possible sugar unit is called monosaccharide, or simple sugar. Some examples include glucose, primary source of energy for cells, and fructose. 2 monosaccharides link to form a disaccharide. For example, sucrose, also known as table sugar, is a disaccharide of one glucose and then one fructose molecule. Lactose is a sugar found in milk, and that is a disaccharide of one glucose and one galactose. Galactose. So it's a little different. Monosaccharides can form longer carbohydrates, molecules such as starch. Starch is the form in which glucose is stored as energy in most green plants. Apart from being a source of energy, carbs can also provide support and structure. So here you see that starches, cellulose, they're made up of lots of these individual glucose and fructose molecules. So we have nucleic acids, carbs, lipids, fats, all good stuff for you. Lipids such as fats, phospholipids, and steroids, hey now, are organic molecules made up of fatty acids and glycerol molecules. They have a lot of functions. They can serve as a stored form of energy in living organisms. That's why some, we store fat in our body to use as energy later. Phospholipids are part of a membrane that helps protect the cell. The cell membrane is also called the phospholipid bilayer. And this bilayer acts as a semi-permeable membrane, which is some things can get through it, other things cannot get through this membrane. And the ability to select molecules helps maintain the cytoplasm in the cell. Some fats our body actually does not make, and we need these fats from food, other substances. The fats from food are necessary for the formation of healthy cell membranes and the proper functioning of the body. For this reason, they are called essential fatty acids. They're fatty acids that are essential. We need them to continue existing. And you can find these essential fatty acids in eggs, leafy greens, beans, and nuts. Here we see the glycerol and the fatty acid structures. And then we have proteins. So you'll recognize all these terms from the food we eat. Protein, fat, carbohydrates, and then nucleic acids or something else. Proteins, they're made up of long chains of amino acids. These amino acids link together by a certain type of covalent bond called a peptide bond. Peptide bonds for proteins. Think of P for protein, P peptide bond. And these proteins are found all throughout your body, in your hair, your nails, your muscles, bones, tissues. Almost every organ has proteins. They constitute about 15% of your total body mass, actually. And these proteins play many roles throughout the body. They're responsible for providing structural support, bones and muscle. They can build and repair tissues. They help with cell growth and your metabolism in the form of hormones. Finally, they are involved in catalyzing reactions, enzymes. And when you get sick, your immune system produces antibodies. Similar to fatty acids, some amino acids are not manufactured by the body, but must be obtained from food. and these are known as essential amino acids. So it's important to take note that humans cannot exist in and of themselves. They need outside substances to continue existing, like a lot of organisms on Earth operate this way. Here in this lesson activity, you're going to watch a video and then answer some of these questions. Assume Deb eats 3 150-gram bags of potato chips each day. Using the food database from the USDA to calculate Deb's calorie consumption and the number of grams of protein, carbs by difference, and the total fat that she eats. Go ahead and pick any brand of potato chip, whatever your favorite is. I know Lay's is like the most popular, but type out the brand in your answer because it can affect the numbers differently. Different brands use different amounts of ingredients, and that can affect how many proteins, carbs, and fat wind up in the end product. And now we're going to look at calories because this is important. People, watching your diet is a big part of living your life, living a healthy, relatively healthy life. But consider a protein. There's 4 calories per gram. Carbs and or sugar, basically the same thing. Just carbs are more complicated. Sugar, same thing, 4 calories per gram. Fat is 9 calories per gram. So fat is a lot more dense. You get a lot more calories per gram. Here it states that most adults are recommended to eat 45 to 65% of their diet in the form of carbs. Proteins make up 10 to 35% of their diet, and then fats make up 20 to 30% of their diet. So you're going to calculate if Deb eating 3 bags of potato chips, does that correspond to this? Is this anywhere near what she's eating? My guess is not. There's not a ton of protein in potato chips, but I'll let you do the calculations on your own. And now we're going to look at careers in science. Medicinal chemist. I had a friend in college that was in chemical engineering, but she was also interested in the medical field. So this is kind of like up her alley. Pretty cool discipline, actually. Medicinal chemistry is where you study organic compounds and materials and try to design and or discover new drugs. So using biochemistry, you are discovering and synthesizing new pharmaceutical drugs. And you could also improve existing drugs and make them less harmful in some cases, because I know a lot of drugs may have side effects that are just as bad or not, or even worse than what they're trying to treat. So through biochemistry, if you're able to make a drug less harmful, or you find newer drugs that are better for humans to take, that's awesome. For example, a medicinal chemist could work on developing a drug that targets only cancer cells and doesn't damage healthy cells in the body, which would be Great. You see, in science, we try to make improvements, and sometimes along the way, you look back and wonder, oh my gosh, we really treated things with this subpar, strange way of things. Like in the future, I think we're going to look back and look at perhaps chemotherapy as very old school. Like, oh, you did what to people with cancer? But for now, it's still one of the main methods we use today. Medicinal chemists typically work with pharmaceutical companies, educational institutions, and government agencies. They can work in labs with lab personnel, or they can work with non-lab employees, such as drug reviewers. Drug reviewing involves determining how much of a drug is necessary and effective. Usually you want to use the least amount of drugs possible to fix the problem, because high dosages of drugs can negatively harm a lot of people, especially some current pharmaceutical drugs that were prescribed to people unknowingly or maliciously, some would say. To perform their duties, medicinal chemists need to work with experts from other fields. They work with biologists and microbiologists. Microbiologists, they study very small microorganisms. They can also collaborate with pharmacologists who study the effects of drugs on humans. And they could also work with toxicologists who study the effect of chemicals that are hazardous to living organisms. So creating a drug can be a very difficult balancing act. You want to find something that's effective, that fixes a problem in a human, but does not negatively affect them more so than it helps, you know? But we are given another question that you are asked to respond to. Some of the most promising treatments for cancer are targeted therapies. Use information from credible websites to explain how targeted cancer therapies differ from traditional chemotherapies and describe why these therapies are an advancement in medicinal chemistry. So chemotherapy is very intense, but it can affect organs that are not being threatened with cancer or cancerous cells. The idea of chemotherapy makes sense, right? You're trying to kill cancerous cells and cancerous masses, but sometimes that can harm tissue that is not cancerous, and it can make people quite sick. But if targeted therapies become the new norm, and I'm sure they will eventually, you will be able to target specific cancer cells and cancerous tissues without damaging anything around the area, the targeted area. So hopefully this would lead to cancer patients not suffering so much through chemotherapy. If you know anyone that has had cancer, like my grandmother and her sisters, it can be rough. Losing your hair, just feeling like crap all the time because you're technically being poisoned. You're being poisoned, but you're poisoning the cancerous cells, and yeah, it's rough. If you can avoid chemotherapy at all, if at all possible, you should do so. And if targeted therapies are the way to go, then that should be the way to go. And yeah, here's the sample answer. Chemotherapy drugs destroy cells that grow and divide rapidly, which is cancer. Cancer is the uncontrolled growth and division of cells. However, in addition to the cancer cells that replicate rapidly, yeah, they also kill normal, healthy body cells. And that's why these side effects can be dangerous. Targeted therapies, they are more specific and they target, it's in the name, they target cancer cells and reduce the damage to healthy cells around the cancerous region. And the targeted therapies may be less toxic on the body overall, even though side effects still occur. So that's great. Chemotherapy is quite toxic, the method through which you're killing cancer. So if you can find a more targeted, less toxic way to go about fighting cancer, that's perfect.
Hello.
Oh my gosh. Let's pause that. But yeah, here's a summary. Just talk through that. I'll let you look through that on your own. But yeah, that has been Intro to Biochem. I think biochem is pretty interesting. If you're interested in learning more about biochemistry, go to YouTube, look up biochemists, experiments, interviews. My roommate really enjoyed the biochem classes in college, less so than the organic chemistry, but biochem they liked. So I hope I added some additional information that you found helpful or interesting. And yes, have a great rest of your day, and I will see you later. Bye.